Bismillahirrahmanirrahim. My name is Amna Irfan. I'm from the Department of BS Biotechnology and my ID is 023. The topic of my presentation is reaction rates and temperature, the Arrhenious equation. Now, first of all, I will tell you about temperature and its importance. As we know that the rate of reaction depends on both reactant concentration and the value of the rate constant. Still another factor that affects reaction rate is temperature. Everyday experience tells us that the rates of chemical reaction increase with increasing temperature. Familiar fuels such as gas, oil, coal are relatively inert at room temperature but burn rapidly at elevated temperatures, means there is a specific temperature for coal, oil and natural gas to burn. Many food last almost indefinitely when stored in a freezer but spoil quickly at room temperature. We'll have another example of metallic magnesium which is inert in cold water but react with hot water immediately. As a rule of thumb, reaction rates tend to double when the temperature is increased by 10, and if we triple the temperature, the reaction rate will also become triple. According to understand why reaction rate depend on temperature, we need a picture or model of how reaction take place. According to the Chlorine theory model, a bimolecular reaction occurs when two properly oriented reactant molecules come together in a sufficiently energetic collision. To be specific, let's consider one of the simplest possible reaction, the reaction of an atom A with a diatomic molecule B, C to give a diatomic molecule AB and an atom C. As shown in this diagram that how A plus BC are react and form AB plus C as an atom. An example from atmospheric chemistry is the reaction of an oxygen atom with an HCl molecule to give an OH molecule and a chlorine atom. This is similar with the above reaction, that how O and HCl react and there is formation of OH and Cl. This also represents Chlorine theory model. If the reaction occurs in a single step, the electron distribution about the three nuclei must change in the course of the collision such that a new bond AB is developed. So there is formation of a bond, and after that there is also a breaking of a bond as well at the same time, which is B, the bond C. Between the reactant and product stages, the nuclei pass through a configuration in which all three atoms are weakly linked together. We can picture the progress of reaction as. In this diagram, we understand that how A react with BC and form an intermediate, and then there is formation of a new bond AB and breakdown of a bond BC at the same time, and as a result we'll have the product AB and C as a single atom. If A and BC have filled shells of electron, no unpaired electron or vacant low energy orbital, they will repel each other. To achieve the configuration ABC, then the atom require energy to overcome this repulsion. The energy comes from the kinetic energy of the colliding particles and is converted to the potential energy in ABC. In fact, ABC has more potential energy than either the reactant or the product. Thus, there is a potential energy barrier that must be surrounded before reactants can be converted to products as depicted graphically on the potential energy profile. Here is the diagram which shows the graph between potential energy and reaction progress. The height of the barrier is called activation energy, and the configuration of the atoms at the maximum is potential energy profile, which is called transition state or the activated complex. In the recent diagram, we will see that this is transition state, and this line shows activation energy, which is represented as EA. Now we will discuss the cases. Since energy is converted in the collision, all the energy needed to climb the potential energy hill must come from the kinetic energy of the colliding molecules. If the collision energy is less than EA, the reactant molecules can surmount the barrier and they simply bounce apart. If the collision energy is at least as great as EA, however, the reactant can climb over the barrier and be converted to the products. Experimental evidence for the notion of an activation energy barrier comes from a comparison of collision rate and reaction rates. Collision rates in gases can be calculated from kinetic molecular theory. For a gas at room temperature 298 Kelvin and 1 atm pressure, each molecule undergoes approximately 109 collisions per second, or 1 collision every 10 to the power minus 9 seconds. Means there is a lot of collisions per second. Thus, if every collision result in reaction, every gas phase reaction would be complete in about 10 to the power minus 9 seconds. By contrast, observed reactions often have half-lives of minutes or hours, so only a tiny fraction of the collision led to reaction. Very few collisions are productive because very few occur with a collision energy as large as the activation energy. The fraction of the collision with an energy equal to or greater than the activation energy EA is represented in the figure at two different temperatures by the area under the curve to the right of the E. This is the graph between fraction of collisions and collision energy at different temperatures. The EA is the activation energy in higher temperature and lower temperature. This line represents EA. When EA is large compared to RT, this fraction F is approximated by the equation, which is as follows. F is equal to E minus EA by RT, where R is the gas constant having value of 8.314 joule or kilomole, and T is the absolute temperature in Kelvin. Note that F is a very small number. For example, for a reaction having an activation energy of 75 kJ per mole, the value of F at 298 Kelvin is 7 into 10 to the power minus 14, which is the very least value. Thus, only 7 collisions in 100 trillion are sufficiently energetic to convert reactants to products. I mean, there is a very less amount of collisions in a large amount of atom numbers. As the temperature increases, the distribution of collision energy broadens and shifts to the higher energy, resulting in a rapid increase in the fraction of collision that leads to the products. At 308 Kelvin, for example, the calculated value of F for the reaction with EA is equal to 75 kilojoule per mole, is 2 multiplied by 10 to the power minus 13. Thus, a temperature increase of just 3% from 298 Kelvin to 308 Kelvin increases the value of F by a factor of 3. Collision theory therefore accounts nicely for the exponential dependence of reaction rates on reciprocal temperature. As T increases, 1 by T decreases. F is equal to EA by RT increases exponentially. That's all from my side.